Now let's go back to our old graph and let us try to do nothing but graph searches. And in the graph searches, now what I'll have is, so this was a graph. Now I'll try to solve this problem and I'll add a visited. So I'll say that's my old definition. So let's add a new definition. Now what I'll say is that I need to define the same path with visited. So I say, is there a path from the source S to the goal G? Is there such a path with V nodes which have already been visited? So the nodes in V which have already been visited, and of course what I'll do is the same thing. So S to G, there is a path if there is a link from S to X, and there is a path from S to G. So I'll write it down directly. If there's an edge from S to X and there is a path from X to G, and that means there is a path from S to G. And the only thing that I'll add in around over here is that of course X is not a member of V. So let's add in the V things around over here as well. So that's a V and that is a V. Now when I do the recursive call, then I have already visited X. So I have my old set of visited nodes and now I have visited X as well. Remember previously when things were extracted out of the fringe, then they were added into visited. Now we're going by the classic thing. Even when things are being put into the fringe, it's being added to visited. There's no optimality as of now. We could do that. Okay, so we of course for this we need the definition of not. So that's how not is defined. So the definition of a not P, which holds whenever P holds. So if P holds, then not P is a fail. Otherwise, so that's my otherwise. So otherwise there I'll have to add a mutually exclusive rule. Mutually exclusive. Otherwise, P will always succeed no matter what. You could also add a semicolon because it's too, I was saying that you can use semicolon in all the programs to mean or. I was redefining because things were getting out long. Now things are not getting out long, so I can use, and if you use this, that's the internal Prolog not operator defined exactly in this way. Remember, it's not as a classical sense. Whenever fail happens, the backtracking completely stops. The backtracking completely stops. So with this, now let us define our new path very quickly. So I say a path exists from S to G using the visited nodes V. If and only if there is a edge from S to X and there is a path from X to G using the visited nodes which are given by X added on top of the old visited nodes. And of course I'll have to say not a member of. So X is not a member of my visited. X is not a member of my visited. And of course, what you can also add now is that the fact that there is a path from S to V if there is a edge from source to goal. So if there's a link from source to goal, you can obviously get in from the source to the goal. You added something on top of a V. You added something on top of V using this list specification. So a new list which has its head as X. Let's do some quick queries part. Let me have a look at the graph, of course. So is there a path from A to B with the new definitions? Okay, singleton variable V. I don't care about V. And here I'll have to specify V. So initially only A is a member of V. Yes, there's a path from A to V. Let's say, is there a path from A to D? Yes, there's a path from A to D. Is there a path from A to E? Yes, there's again a path from A to D. Is there a path from B to A? No, there's no path from B to A. Again, what you could do is that because the source was already added into visited, a constraint is also from this little thing that your X, just to tune it up a little bit and also to tell you what is not equal to. So X cannot be G, because if you look at it, if X is G, you're asking, is there an edge from S to G and a path from G to G? You would have got an answer from here being more specific. So I just had X is not equal to G as a constraint over here as well. Now, of course, we've answered the queries and the result seems to be coming both when there is a path and there's not. Luckily, we did not incur in an infinite loop. Now, what if you need a path as an answer? So, what if queries, instead of just taking the visited, need to be, is there a path from S to G using the visited nodes V? If there is, please return me up. I cannot say path is equal to, so I say the path will be the output channel over here. And of course, what we could do is not add any line of programming and see how does backtracking really work. So let's take a dummy path A, B, C, D, and E. Remember, Prolog is using backward chaining, which is indirectly backtracking. So I say, is there a path from A to E using the visited sets, which is just the source A, a path P? I say it will of course exist if there is a edge from A to B and there is a path from B to E using visited A comma the new X, which is a B, and the path P. This luckily is satisfied, so I need not venture in. So is there a path from B to E? It only happens if there is an edge from B to C and there is a path from C to E using visited AB and the new X that was returned. So actually this is returning the substitution X is equal to B and X is equal to B here, X is equal to C. Here the substitution is coming, which is being enforced over here. So with the path P, is there a path from C to E? Yes, there is. If there is an edge from C to D, and so X is equal to D, substitution will get returned over here. There is a path from D to E using the visited sets A, B, C, D with a path P. So I again ask, is there a path from this if there is a edge from D to E? Yes, there's an edge from D to E. So this time I'm going by my base condition, which is right here. I'm not going by the other condition, which was recursively dividing it into a similar problem. And if you look at it closely, A, B, C, D, E, I've got the answer over here itself. The only problem is that I need to somehow store it. So I just say P is equal to the V at the last step, or P is equal to V at this step around when it succeeds. So I say I also need the path. I also need the path. So when I go normal, I don't do anything else. At the last backtracking, what do I do is I say P is equal to V, and of course I won't do it around over here. I will say V. So my answer is the list of nodes in V in exactly the same order, and let us run that up. So I have my graph around over here. So I say, is there a path from A to E? Oops. Using the visited set A, and the path has to be P. So give me the path. So the answer comes out to be A, B, C. Firstly, it's coming in the inverted order. A, B, C, and secondly, goal is not being added. The goal is not being added, I actually saw it around over here itself, that the goal was not being added. So let's add the goal manually. So the answer is goal added on top of V. And now do I get the correct answer? Oops, the listed set is A. So ECBA, let's check if that is the correct answer. Firstly, it's inverted. So ABCE. Oops, yes, that is the correct answer. Is there some other part? ABDE. Remember, it's inverted. So ABDE, that's also the correct part. ACE, that's also correct part. False. Remember, the visit constraint is there. So you cannot visit one node twice. That constraint has been programmed. That's why you're getting answers as, that's why you are not going into infinite loop whenever there is no path. So now I just need to correct the little thing up that I am getting the answer, but the answer is what is unfortunately a negative or reverse. So the answer is always coming out to be a reverse, and somehow I need to add that up. One way to do that is that instead of adding elements to visited at the start, if I add it at the end, I'll get my answer. So let's do that. If instead of adding elements to the start, I will add them to the end, A added to the end, when I got the substitution x is equal to b, I add up b at the end. Okay, here I had already added up towards the end, and that's why I was getting the correct answer. So I always add it at the end. Unfortunately, there's no such function, and I will have to make add up. So I say add at end. I'll have to make such a function. So let's quickly make it up. So add at, oops. So I need to add x to the list at L at the end, which gives me the answer as a list L1. So x added to the list L at the end gives me a new list L1, and remember I cannot say L1 is L and A X. This head can be one constant element, two constant element, three constant elements. It cannot be variable, general list L. So this one doesn't work. Otherwise, my work was absolutely very simple. So I will have to do it by recursion, of course. I love drawing a lot of lists. So the list L, I will of course recurse over it. So I will maybe break it down into H and T, and X needs to be added right around over here. So I won't care about the head. I will just say add at end. X should be added at the tail. Head, I don't care about it, just throw it up. That will in fact give me some answer, and X added at the end will give me some answer. So let's temporarily add X at the end. And I love taking new variable names. So when X is in fact added out right at the end, let us say that we get in a new answer, which happens out to be a T2. So my answer is a T2. When X is added to T at the end, the answer is T2. So what is my answer? L1. So my answer L1 is, what is this list? So L1 is the head remains as it is, same as L, and after it I have got a T2 added. Of course I will put it down over here as well. Instead of saying L1 is equal to, I'll put it down over here. So I say X added to a L produces, L is in terms of a head and tail, it produces a new list. Head remains as it is, the tail is changed to a new tail, and the new tail is given by, so the new tail is the output of adding X to the tail of the input list to create a new list T2, and this is what is add at end. The base case, of course, is I'm recursing on the list which will get empty. The answer, no surprise, will be X added towards the end of an empty list is just a list X. So let's do it pretty quickly, and let's see if we can do that. So X added to a list of head and tail. It produces H, head remains unchanged, and a new tail T2, where the tail T2 is at that end, X added towards the end of T produces T2. And my base condition, empty list, X added to an empty list, it produces X as a list. Let's check it up at that end, 10, 1, 2, 3, 4, 5, produces the answer L. So what is L? L is 1, 2, 3, 4, 5, which is correct, and of course I do have my 10, which is added right after it. Now you will see a little thing around over here, which is the weird bracketing, of course, and this is because of an obvious error, which is, it's not here, it is here. Yeah. So it just produces one answer, which is 1, 2, 3, 4, 5, and 10. That is absolutely correct. So now let me define that up. So my condition is right around over here. So now instead of adding X at the start, I will add it at the end. So let us say my new visited, which is V2, is add at end what X added at the end of V produces a V2, and of course it's prolog, so we write it like this. So V2 will automatically get its correct answer right over here. I will have V2 as a result of this. Once I have V2 over here, then I need to send V2 as the input. So let's say path from A to E using the visited sets A gives me a path which is B. So I get E ABC. The good thing is that I've got ABC as correct so far. The problem is ABC is correct. Now the problem is E was wrong. So let's correct for E as well. So instead of adding G to V, I say the path is P. And let's calculate P over here. So P is equal to add at end, goal added at the end of V. And of course, that's how I write it into Prolog. Goal added at the end of the visited list gives me the path P. So ABCE, that's correct path. ABDE is also correct, ACE is also correct, and these are the only paths such that every element is visited at once. Now